Good afternoon, my name is CarolineDesouza, and I'll be discussing the paper that I read with all of you today. It's called Incremental Elasticity for Array Databases. The paper discusses both the design and implementation of elasticity for an array database, along with the challenges that are associated with this implementation and design. So what is elasticity? For those of you who don't know, elasticity of data refers to the flexibility of both its data model and its clustering capabilities. Elastic data stores have the characteristics of tolerating greater numbers of data models and an ease for managing data clustering. The research motivation behind this paper is based on elastic databases that apply to the scientific community because they gather tons and tons of data, and often that data cannot be discarded because it needs to be used for research evaluation. So the focus here is on determining when to expand a database cluster and how to partition that data within it. So the problem that prompted this research is that current relational database management systems are inelastic, and so they're impractical for the scientific community. And as a result, many scientists resort to creating their own database management systems to address these research needs, or their research needs. This can be expensive because it entails a lot of overhead and a lack of customization, because of so much customization, this leads to a lot of different scientists having different platforms which won't be interoperable across the industry. So this actually impedes the sharing of information across the industry and across amongst different scientists. So this problem is only getting worse because data keeps coming, right? So we have more data nowadays than we even know what to do with. In the paper, they discussed a couple of examples, which is the Sloan Digital Sky Survey. They've generated over 25 terabytes of data over the past 10 years. There's also the Large Synoptic Survey Telescope, which estimates that it'll produce about 20 terabytes of data every night. And that's a lot of information for one database to handle. Hence the importance of this work, because it allows for database expansion, which in turn yields more flexibility for scientific databases. So scientists now won't be limited to a no overwrite storage model, which means that a no overwrite storage model basically is what they're using now, which entails them having to delete previous information to make room for new ones. So with this research that's being conducted on this paper, scientists can conduct uninterrupted research without having to discard previously recorded data to make room for new ones. So some of the novelties that this paper brings about is that significant research has been done already concerning the elasticity of relational database. That's not a first. However, what they've done here is they address the elasticity of array databases with long-running queries with a focus on storage SKUs, and this is something that past works have not done. Those a lot of works that are that have addressed this have only addressed transactional workloads, not arrays or analytical queries that run for long periods of time. So their contributions include extending the partitioning schemes for SKU awareness, n-dimensional clustering, and incremental reorganization. They also introduce an algorithm for efficiently scaling out scientific databases, and they evaluate the system on real data using a mix of science-specific analytics and conventional queries. Some of the challenges that they came across in this research was making sure that every database partition was approximately equal in size. So the database that the researchers used in this paper are what they call read mostly, or pretty much read only. They're not changing the data on the system with the exception of adding new data, but that's not really changing the information, you're just adding new things, so new data. So past works address write-intensive queries, so queries and data types that are being changed in many ways, and that's not what their focus is on here. Some of the limiting factors that they came across were the input and the output and network bandwidth. Another challenge that they came across was identifying adequate hardware resources. So the way that the researchers went about conducting this experiment was to survey 2 use cases where that are real world and practical, so that they could derive their workload data models for this platform. They used data from NASA's MODIS, which is the Moderate Resolution Imaging Spectroradiometer, and this is an instrument that's aboard NASA's satellites that records images of the Earth's surface every 1 to 2 days. They also used data from ship tracks using the U.S. Coast Guard's automatic identification system. And with this type of data, both of them having 3-dimensional data types, which is latitude, longitude, and time, they tested a series of algorithms using 2 types of workload benchmarks. With this data, they tested a simpler, more conventional type of query, which evaluates database performance on cell-centric queries. So these are simplistic, they're not calculation intensive. And then they also use more complex science-oriented analytics, which are going to be more mathematically intensive and such. And it measures database performance on domain-specific processing for each workload. The incremental reorganization schemes that they discussed in the paper were classified based on 4 features. So they used incremental scale-out, fine-grained partitioning, skew awareness, and multidimensional clustering. After this classification, they applied the leading staircase algorithm, which is used to scale the database elastically. And it also has a set of techniques for fine-tuning the database, the algorithm. So the name of this algorithm, leading staircase, is based on the observation that the database expands its cluster size in a series of steps. So the elastic planner then projects future node demand via proportional derivative control loop based on the last S workload cycles. This projection then adds K number of nodes and increases the database capacity to serve the next P workload iterations. This method models the needed database expansion rate for both the current and projected workloads. Conclusively, their results found that fine-grained partitioning had the best load balancing, incremental scale-out, skew awareness, and multidimensional clustering had faster query execution because of spatial clearing, but ultimately multidimensional clustering performed the best. So with all of their experiments in mind, the researchers concluded that incremental handling of data placement and node provisioning produces significant efficiencies for expanding array databases. So that's really all I have for you guys today. The work that these researchers conducted definitely show that relational databases can be expanded, and that there are productive ways of going about it despite the research that has been done to the contrary. Thank you very much for your time.